Hey there, my name's Gary Sims and this is Gary Explains. Today I want to look at how you can build a supercomputer using a cluster of Raspberry Pi boards. So if you want to find out more, please let me explain. Now, modern day processors are multi-core processors. So even on a Raspberry Pi, you might get 4 Cortex A53 cores. In smartphones, there might be 8 cores. In laptops, 4 cores. In desktops and servers, maybe 16 cores, 32 cores, just depending on how much money you want to spend. Now, when you write a program that has to do lots of computing intensive tasks, the more cores you have on that processor, the better. So if you can split up your task into individual chunks, and then you can give each core that piece of data, then they can work individually and then come back and give you a result. And that's multi-threaded programming. Now I have a whole video on multiprocessing and multi-threading and multitasking, and I'll leave a link to that in the description below. Now the problem is if you want to calculate something that's very, very complicated, predicting, weather systems or, all kind of things that they do with supercomputers, then just having 16 cores or, even 32 cores is not going to be enough. You need thousands of cores. And that's where a supercomputer comes in. So a supercomputer in this context is a set of individual nodes. So each one is a computer, it's got its own operating system, it has a CPU, multiple CPUs sometimes, with multiple cores in them, okay, and that they run, but they're all connected together. So you have all these nodes together, and accumulatively, together, they might have, let's say, 1,000 cores or whatever it is that you're aiming for. Now the problem is when you write a program for multi-threading, you're running onside that one computer. So you compile the program, you run it, and it runs there. When you have all these nodes, you have to have a way of the computers to talk to each other and to share out this task. And then once they've done their chatting and their processing, they can kind of come back and give you the results. So that takes a different style of programming than just maybe traditional multi-threaded programming that you might get on a PC or a laptop. And so there are 3 stages in building a supercomputer. One is you need the actual hardware. The second is you need to actually do some setup. And the third is you need to write your program. So let's look at those 3 stages. Now, obviously, in a real world supercomputer, you're talking about lots and lots of hardware that's got lots and lots of cooling, and it requires lots and lots of electricity, and it costs a lot of money. But you can actually build the concept of a supercomputer using something simple like the Raspberry Pi. Then you don't have problems with price, you don't have problems with electricity bill, you don't have problems with heating, but actually you can still replicate the theory and the basis behind supercomputing. So in this example, I've got myself 4 Raspberry Pi Model 3 boards. I've got them together here in this nice little rack, and they are all connected using USB power. So it's very simple to get it all up and running. They also all have wireless built into them, so that means I don't have to run an Ethernet cable to each one. I can do it over the wireless network. So once you've got the hardware together, the next thing is to do the setup, the software configuration. And to do that, each of these boards is running a Raspbian, and also I've done 2 important things. One is I've made sure that each board can talk to the other board using secure shell without a password, but using public and private keys. Now, I'm not going to go into how you set that up now. There are lots of tutorials on the internet, but the idea is basically this: you should be able to copy files using SCP or log into any of the nodes in your cluster using SSH with private public key, which means it doesn't ask you for the username, doesn't ask you for the password, it just connects straight away. And that's needed because when all this data is flowing about, you need authenticated, secure ways of transmitting that data without you having to type in passwords and worry about, is this message allowed to come from here or not? So you have to get that set up first of all. And the other important step is you have to install some kind of MPI library. Now, MPI is the message passing interface, and this is a standard way of sending blocks of data from one node in a supercomputer cluster to another. And there are various different implementations of it. I'm using MPI for Python, which is a way of allowing MPI messages to be sent across a supercomputer cluster just using the Python programming language. Then the final step is you need to write the program itself. Now, it's not like writing a normal program where you just go around in a loop and say, hey, let's do this. You can't just say, oh, please magically run this on all the nodes in my supercomputer. You need to write your program in a specific way that it knows it's running in a cluster, and it knows it's got these other nodes that it can talk to, and it knows to send that information to them, and it knows to gather that information back in again so that it can analyze the final results. So what I've done is I've wrote a program that allows me to check if a number is a prime number or not. And I'm going to do that by sending out that number to one of the nodes and getting it to check it and then send the answer back. In fact, the way it works like this, with 4 boards, that means I've got 16 cores, with each board having 4 cores. So the MPI program sees it as a 16 node setup. And what I actually do is I create an array of 16 numbers, and then you can say to MPI, please scatter that across the nodes. And what it will do is it will send one number to each of the nodes, which really is actually 4 nodes, each with 4 cores. And then at the receiving end, those nodes will receive that number and say, right, this is my number. I've got to check if that's prime or not. It will check if it's prime or not, and then it will send back the result. And so the master node gathers in the number. So these are 2 of the important words for MPI: scatter and gather. Now, there are many actually different models in the MPI setup and the different ways of using them. This is a simple way of showing how you send out the data and bring it back in again. Now, actually, if you run that for just one prime number, it's actually really slow. It's actually slower than if you did it on just one node. And the reason for that is to get this running, each of the nodes has to first of all spin up and be ready to receive these MPI messages. You then have to send the MPI messages over the network. It then has to do the calculations, then has to send the messages back. They have to be gathered in again, analysed, and the results printed out. So the overheads of doing all that just to check whether one number is prime or not is really, really high, particularly for checking for lower numbers. You know, is 7 a prime number? Well, I send the message over a network, it works, it sends it back again. Well, that takes forever compared to me just checking locally if 7 is a prime number or not. So what I've done in my program is actually I've created a huge chunk of data that's maybe got 1,000 numbers for each of the nodes, and then that gets scattered across all the nodes and says, please check these 1,000 numbers, then come back and give me the result. Now, even this method itself is not very efficient. There's a lot of numbers you've got to send out. I could maybe, for example, send a beginning and end of a range. Maybe that would be easier. But this is the way I've chosen to demonstrate that you start with a big chunk of data and then you scatter it across the nodes in your supercomputer. Finally, once all the nodes have processed 1,000 numbers each, they come back and they tell the master node, here are the results. And then very quickly it can say, well, these are all the prime numbers from the list that has been checked. Okay, so there's 2 things in quickly. One is this program will be available on my GitHub repository, and you will find a link to that in the description below. And now let's head over to my cluster, log in via the command line, and let's see this actually running in real life. Okay, so what we have here is 4 terminal windows, each one connected to one of the 4 boards. And the one here in the top left is the first one, second one here on the top right, third one on the bottom left, and fourth one on the bottom right. And what we're going to do is show you that each one is basically not doing anything, it's idle. You can see here the 4 processor cores, and each one is pretty much doing nothing. So what we're going to do first of all is I'm going to show you that I have here a program written in Python. Okay, that is actually, you'll find it on every single node. So if we go down here to number 4, for example, we can do exactly the same thing. And we can see that the same script is there. And that means that when it runs across the supercomputer node, the same script is run on each of the 4 different machines. We'll put this one back now into HTOP. Okay, and so the first thing we're going to do is we're going to run this script just on one node. Okay, and the way you do that is you use this MPI exec program. The time bit here at the beginning is a way of seeing how long it runs, and then it says basically run Python, and then this program that I just showed you. So it will run now just on one Raspberry Pi. So notice it says there are only 4 cores. Okay, and it's starting to find the prime numbers. And if we look here at the other devices, we can see their activity has remained at 0, very idle. There's nothing going on. And this will take about 30 seconds or so to complete as it finds all the different things. And the other 3 nodes here are doing nothing. It's all happening just on this one node. So it's about to come to its completion now, and we'll see how long that took. 92,000 prime numbers found so far, 101,000 found. It should find 109,000. There you go, 926. And it took 33 seconds. Okay, so that's what it does if you run it on just 4 cores on one Raspberry Pi board. Now, before you run this on the cluster, you have to define a file, which I've called cluster file, which has got the 4 names of the different, the IP addresses of the different clusters. So here we can see 33, 43, 53, and 47. So here, if I do an IP address show WLAN 0, we can see here that this is 47. Number 47, which is the last one here. If we go down here to this bottom one here in the bottom right hand corner and run the same command, IP address show WLAN 0, we can see here that this is 53. Okay, and the other 2 are also listed as in that cluster file. Okay, so now we want to run it across all the different nodes in the cluster. So what we do is we use this command, the same again, MPI exec, but now notice we have this pit here that talks about host file, cluster file, which points it to that file I created with those list of IP addresses. Okay, so now when we run this, we'll be able to see that it runs across all the different nodes. So let's just fire that off. And the first thing to notice now the other devices here, the other boards are all starting to run at 100% as they are being used. Notice here it now says total cores 16 because it's running across all of the different things. And if you look here on this one, for example, you can see these first 4 tasks were the Python task, and there it has, it's finished. And it finished in 16 seconds. Okay, so that was twice as fast. Now, some of that is because of the overhead. If this was running for much longer, for several minutes, for several hours, then that overhead would become negligible. But what we saw was that by running it across all 4 nodes in the cluster using 16 cores, we got a much, much faster time. And that is the essence of how you run supercomputer programs. Okay, so there you have it. There you saw the program running there, and you saw that it is quicker using the cluster. I'm sure I could actually make it more efficient to make it even quicker on the cluster, and it would gain efficiency even more so as you got to even bigger numbers. But that's how supercomputers work. And so no matter how complicated the task, you still have to break it down into smaller tasks, and those smaller tasks are run on the individual nodes in your huge supercomputer. Now, of course, you could build a computer much more powerful. You could do this using PCs, you could do this using laptops, but of course then you do have the issues of cost, electricity, and of cooling. Whereas if you did this with 4 Raspberry Pis, even 10 Raspberry Pis or 20 Raspberry Pis, you get the idea of how to distribute a task across many nodes, and then you can verify that. And then one day, if you do actually get access to a real supercomputer, you can run that program on there and see how quickly it really does run. Okay, that's it. My name's Gary Sims. This is Gary Explains. I really hope you enjoyed this video. If you did, please do give it a thumbs up. Don't forget to subscribe, and well, that's it. I'll see you in the next one.